It's a great pleasure.
Right. Okay, so can you please put your slides on?
Mm-hmm.
And again, you have 25 minutes and 5 minutes for questions. And okay, Marcin Magdziarz from Wroclaw will talk about stochastic representations of processes with resetting. Please, Marcin.
Okay, thank you very much once again. I'm happy to be here virtually, but still it's a great pleasure. And my talk will be about processes with resettings. So in the past few years, this type of processes became very popular, especially in statistical physics, also biology, for example, with a number of interesting applications and also some theoretical results. And in this talk, I will try to show another approach to processes with resettings, which is based on the appropriate stochastic differential equation. I will try to show you that this approach is very useful since it produces very explicit, very nice results related to processes with resettings. So quickly, my outline of my talk, I will start with some examples and with the definition of processes with resetting. The main part will be about stochastic representation, so the stochastic differential equation, which I will analyze and which describes processes with resetting. So a few results related, lemma, and using lemma, you'll get the nice and simple formulas for generating functions, Fourier transform, PDFs, infinitesimal generators, and the corresponding Fokker-Planck equations, and many, many more. And the last part will be about extensions of the classical Brownian motion with resetting to the non-homogeneous resettings, non-homogeneous in time resettings, and also replace the Brownian diffusion by, let's say, subdiffusion to make something fractional, since the workshop is about fractional equations. Okay. So let's start with definition, maybe with a typical trajectory of Brownian motion with resetting. So the idea is very simple. We have Brownian trajectory, and in certain random moments of times denoted by S1, S2, and S3. So the trajectory is pushed back. It jumps to some predefined point, which is denoted here by XR. This is the so-called resetting point, and then it continues the diffusion, and again the resetting point, and so on. So this is visual, very simple idea. And in the standard setting, so we have this diffusive process is a Brownian motion, and the waiting times between consecutive resetting events are exponentially distributed with certain parameter R, so they correspond to the Poisson process. So therefore, this type of resetting is called Poisson resetting. More formal definition, I took it from a very nice recent review paper from 2020 by Evans and his collaborator. So this is the recursive definition of a process Brownian motion with resetting. So we have some starting point, x0, and then we have this recursive relation. So the position of particle in time point t plus dt is equal to the resetting point xr with some probability r times dt, and the position at t plus dt is equal to the current position plus Gaussian noise with probability 1 minus r dt. Having this recursive relation, we can write out the corresponding master equation and derive the Fokker-Planck equation, which describes the dynamics of the PDF, the density function of this Brownian motion with resetting. So this is very similar to the classical diffusion equation, so the heat equation, but here we subtract part of the mass of the distribution because of the resetting events, and we add some mass of the distribution to the point xr again because of the resetting. So this delta is the delta. So these are the typical approaches which we can see in the literature. So the Fokker-Planck equation and this recursive relation and the master equation related master equation. So these are the typical approaches presented in the literature. Because before I move to this another approach based on stochastic differential equations, a few examples of applications because they are very interesting, at least for the people in biology, in medicine, psychology, and so on. So the first example is from 2014 paper. There are many more as this type of examples, and it's related to foraging patterns of animals with relocation to home zone. So this relocation to home zone, it corresponds to the resetting moment. So imagine an animal looking for some target. It's usually a food. So it is searching for a food, and when it gets dark, for example, it moves back to the home zone. So this is exactly the type of displacements which is related, which is very close, so which corresponds to the diffusion with resetting. And it seems that this relocation to home zones is beneficial in the sense that if we are looking for a sparse target or just one target in some area, so this relocation to home zone, so this resetting times, they make the time to find the target much shorter compared to the standard diffusion, which is quite surprising. Another example is a very nice paper from 2020. The authors of this paper, they constructed a experimental setup in which we have some particle which is suspended in some fluid and it diffuses. And from time to time, using optical tweezers, this particle moves back to the origin. So these are the trajectories, and the red lines are the resetting moments when the particle is pushed back to the origin. So this is the origin of the motion. So another nice example of diffusion with resetting. Another example comes from visual search. Paper from 2020. So this is related to locating a face in the crowd. So the authors of this paper, they have shown that if we are looking for some certain spot, for example, a face in the crowd, so we are moving like, let's say, diffusion or maybe anomalous diffusion, but from time to time, we tend to go back to some initial position with our eye. So this is also exactly an example of process with resetting. Okay, so we have much more examples. So you can find them, for example, in this review paper by Evans from 2020. And now let's move to the main part. So let's start with some definition. We have TIs. They will represent the waiting times between consecutive resetting moments. Sn are the moments of resets of the sums of TIs. In the usual way, we construct the corresponding counting process, NT. So NT is just the number of resets up to time t. When TIs are IID exponential, then it's obviously Poisson. And then we introduce the following stochastic differential equation. This equation of the following form. So this is equation number 1. And we'll argue that this describes the dynamics of a stochastic process WT under resetting. So indeed, if we take a look at this part, so this is the NT is a counting process, it counts the number of resets. So the DNT, it can be only 0 or 1. It is 0 when there is no resets. So this part disappears, what is left is only W. So when we have no reset, then we have, let's say, only Brownian motion, when W is Brownian motion. But when it is 1, so when D and T is equal to 1, so when we have resetting point, then we subtract the current position of X, and we arrive at the resetting point R. So indeed, this simple stochastic differential equation, it can describe a dynamics of a resetting process, of any reasonable stochastic process W under certain resetting given by any counting process. And so it's actually very general, but I will try to show that it's extremely useful. And it's, I would say, it's a proper tool in the analysis of resetting processes. So let's start with a standard setup. Standard setup meaning that we have W is a Brownian motion, so the Wiener process, one-dimensional Brownian motion, and T is the standard Poisson process with some intensity R greater to 0. So we can obviously easily derive the corresponding Ito lemma. So for appropriately smooth function, we have the following Ito lemma, which is the generalization of the classical Ito lemma for Brownian motion or the diffusion processes. And having this Ito lemma, we can get a lot of nice and explicit results. For example, if we use the Ito lemma for the following function, exponential function, and then when we take the expectation, then we arrive at the following ordinary differential equation. Solution of this equation with appropriate initial condition, it's the moment generating function. So the moment generating function for Brownian motion with Poissonian resetting has the following simple form. So we can see it's only elementary functions. Again, the same way we can derive the Fourier transform, just change the function for which we use the Ito lemma, and we get the following Fourier transform corresponding to Brownian motion with resetting. What's interesting, that this type of dynamics has stationary distribution. So if we take limit when t goes to infinity of our characteristic function, we can see that this whole part disappears because of this exponent here. And what is left is only this expression here. And this is the Fourier transform of a very well-known distribution. So this is the Laplace distribution. So actually the stationary distribution of Brownian motion with resetting is Laplace, with the PDF also well-known of the following form is the exponent of the absolute value of x minus xr. So this xr is the mean. Okay, what we also can do, we can invert the equation number 4, so the one for the Fourier transform, and we also get completely explicit PDF of this Brownian motion under resetting. So it's equal to the Laplace distribution plus some exponent times the PDF of some Gaussian distribution and minus convolution Gaussian and Laplace. So this is the explicit PDF for Brownian motion with resetting. As you can see, we get very nice, everything is explicit using this Ito lemma approach and stochastic differential equations approach. So let's take a look how these PDFs look like. So this is for the case when the resetting point is equal to 3 and when the intensity is equal to 1. So this picture on the left is for small times. So for t equal to 0.1, we can see that for small time we have a strong diffusion component, but we also see an emerging part which is related to this Laplace distribution. And when time passes, this diffusive part completely disappears. So this is for t equal to 10. What is left only is this stationary Laplace distribution. And what's also interesting is that, at least from the point of view of stationary distribution of this process, it's this Laplace distribution is also a stationary distribution of diffusion without resetting, but in the presence of potential of the following form. So if we take the Landrevin equation for Brownian motion with the following potential, so the stationary distribution will be exactly the same. So we can think that this resetting has similar effect, at least when it comes to the stationary distribution, as the potential of the following form. Obviously, so the trajectories look different. So in the case of resetting, we can say that the trajectories, they do not oscillate around any, let's say, equilibrium state. So the trajectories look different, but still the stationary distributions are the same. Okay, so again, we can calculate the generator. So the generator of the stochastic differential equation has the following form. We can calculate the adjoint operators, which is given by the following formula. Having these operators, we can also write down the corresponding Fokker-Planck equation. So this Fokker-Planck equation has the following form. This is diffusive part plus some expression in bracket, which can be simplified easily, and we arrived at the end at the following expression. If we so this Fokker-Planck equation obtained for our stochastic differential equation is exactly the same as the one as I presented at the beginning, which was given as one of the possible definitions of process with resetting. So we get exactly the same result, but using different approach based on stochastic differential equations. Okay, so we were able to get much more results. We could calculate the multi-point distributions, we could calculate the first passage times and many more. It's all very nice, very explicit in most cases. But what's also interesting in the stochastic differential equations approach is that it can be easily generalized. So now let's concentrate on a few generalizations. So first generalization will be by replacing the Poisson process by the non-homogeneous Poisson process. So now W is Brownian motion, still Brownian motion, but the resetting here is not the same given by the non-homogeneous Poisson process with certain intensity function R of t. So the intensity now will depend of time. For those who are not familiar, so this is the definition of non-homogeneous Poisson process. It's a counting process, starts at 0, has independent increments, so it's additive process, but it does not have stationary increments because the intensity is time dependent, so it doesn't have to be stationary. The increments are stationary only in the case when RT is constant, so when n is just a Poisson process. And point number 3 tells us the probability of observing one jump on the interval t to t plus h is equal to the intensity function. So intensity function, let's say that influences the number of jumps that we observe times the interval length plus something small. And the probability that we observe more than one jump is just small. So it's small o of h. So this is the definition. And this is the trajectory of non-homogeneous Poisson process with a intensity function equal to 10 times sine squared. So we can see there are some regions of this trajectory when nothing happens. So these are the regions when the intensity is very small. So when the sine is close to 0, we do not have jumps because intensity is close to 0. But there are also regions when we observe a lot of jumps of this non-homogeneous Poisson process. They are here. And this is when the sine square is close to 1. So using this intensity function, we can actually model any type of time-dependent intensity. So actually, the model is very general. It's very common in finance, especially in insurance models. So this non-homogeneous Poisson process. Okay, and now let's go back to the Brownian motion with non-homogeneous Poisson resettings. Again, the Ito lemma works. We derive the following equation for the moment generating function. So the solution is a bit more complicated because now it involves some integrals. Since this function, intensity function, we do not assume too much about it. We just assume that it's integrable and not negative. By capital R of t, we denote the integral from the intensity. So the moment generating function has this form. So using this moment generation function, we can calculate the derivatives, for example, and get all the moments we want. We can also calculate the Fourier transform, also completely explicit, and even more, we can calculate the PDF in the closed form. In this case, it's not that clear. So the situation with the stationary distribution is much more complicated. It strongly depends on the behavior of this intensity function small r. So we can observe stationary distribution, but in some cases, depending on the choice of the intensity function, we might not observe any stationary distribution. I will show you one example in a moment. Nevertheless, we have a very nice formula for the mean square displacement. So for the second moment of Brownian motion with non-homogeneous Poissonian resetting, it's E2 minus capital R times this integral. So it's very nice. So in some special cases, we can get much more explicit results. So let's consider one such case. Let's assume that our intensity function is power law with some exponent p, which is any real number, and +1 here is only to avoid some singularity problems. So let's consider different cases. For example, when p is greater than 0, it means that this intensity function increases. It increases when time passes, so it means that we observe for large times, we observe more and more resetting events. So the trajectory keeps coming back to this point, resetting point XR more and more often. And as a result, we can get that XT converges in distribution to this constant XR for t going to infinity. So this is first type of the behavior. When p is equal to 0, then R intensity is constant. So this is the previous case. We already know that we observed then the Laplace distribution as the stationary distribution. Now, interesting case when p is between -1 and 0. So in this case, when p is between -1 and 0, then the intensity function goes to 0. It goes to 0, but very slowly. This capital R of t, for example, is then increasing. So at the end, we were able to show that in such case, xt can be approximated for large times by Laplace distribution, and the mean square displacement behaves for large times like t to the power of -p. And since p is between -1 and 0, it's subdiffusion. So actually, this resetting and non-homogeneous resetting is another way of obtaining subdiffusion from Brownian motion. So it's enough to take the intensity function of the following form with p between -1 and 0, and then we obtain subdiffusion. And when p is less than -1, it means that the intensity function quite quickly, let's say, converges to 0. Also, the capital R converges to 0. It means that for large times, we observe less and less resetting moments. So at the end, we just get the standard diffusion. So xt can be approximated by Brownian motion. And also, the mean square displacement is proportional to time. So it's linear in time, like for Brownian motion. Okay, so this example shows that depending that this non-homogeneous Poisson approach can give us well, quite different and quite peculiar, let's say, behavior of Brownian motion under resetting. Another extension I would like to mention is by replacing Brownian motion by subdiffusion. Let's make things more fractional here. So our W now is Brownian motion, but subordinated to the inverse alpha stable subordinator. Alpha between 0 and 1 is the exponent of stability of the stable subordinator. And obviously, we know that the PDF of this subordinated Brownian motion satisfies the fractional diffusion equation. And we are interested in the following process. We have Poissonian, standard Poissonian resetting, but instead of Brownian motion here, we put subdiffusion. So since we have this equation, since this equation works for any stochastic process and any counting process, it can also be used to generate trajectories, to use Monte Carlo method. So this is the corresponding trajectory of subdiffusion with resetting. We can see that it's subdiffusion because we have all those waiting times here, but we also have the resetting moments S1, S2, and S3. So in this case, XR is equal to 0. So again, we can use the lemma approach. It's a bit more complicated because we do not have pure Brownian motion anymore. Nevertheless, this process is a martingale, so the lemma can be derived, and we can also more or less explicitly derive the distributional properties of this subdiffusion with resetting. But now I would like to concentrate a bit more on the problem of heating times, because for me it was, let's say, motivation to get interested in this resetting processes. So let's take a stochastic process y, and t of y will be the first heating time of some barrier A. This is one-dimensional right now. Okay, and let's take a look how this distribution of heating time changes depending on if we have resetting or we do not have resetting. So obviously, when we have Brownian motion without any resetting, then this heating time is Levy distributed. We know that this corresponding probability, survival probability, behaves like t to -1/2. This is well known. We also know, it's known from in the literature, that if we have subdiffusion without any resetting, then the survival probability of the heating time behaves like T2 minus alpha divided by 2. So it's slower, it converges slower to 0 than Brownian motion. And this is obvious because we have these power law waiting times. What's interesting was what was a surprise for me when I derived it, but I also found it in the literature, is that when we take Brownian motion with Poissonian resetting, then the survival probability converges exponentially to 0. So it's much quicker than the power law behavior of Brownian motion without resetting. And I was surprised because I thought that, let's say if we assume that this barrier A is positive for a moment, but we still have all those resetting moments and resetting times, and they pushed back the trajectory back to origin. So I thought it would be more difficult for Brownian motion with resetting to reach this barrier A. So I thought that this survival probability should be even bigger than in the case of pure Brownian motion, and it's completely different. And then I realized that if you assume for a while that A is positive, then this resetting makes it impossible for Brownian motion to make long excursions on the negative half-line. So this is the reason why this survival probability is exponential. So it converges to 0 much quicker than for the pure Brownian motion. And this result also shows that the strategies of animals of foraging and going back to the home zones is very reasonable, because if you want to find only one target or the sparse targets, then this resetting, which corresponds to going back to the home zone, makes the length of this search much shorter. So it's actually very reasonable to go back to the home zone and not only perform diffusion when we want to find something. And when we have subdiffusion with Poisson resetting, so this is the last example, then the survival probability is like T2 minus alpha, so it's quicker than for subdiffusion without resetting, but it can be slower or quicker than the survival probability for Brownian motion. Okay, and I believe this is a good moment to stop. These are the primary results we obtained for the different processes with resetting, homogeneous and non-homogeneous resettings. And these are the references. So this is the paper which is submitted, in which we presented most of the results are shown here. And this is number 2, is a very nice review related to processes with resetting. There is a lot of other papers related to resetting. I would not be able to cite them all, but most of them can be found in this recent paper by Evans and collaborators. The book by Oxendahl and Sulem is a nice reference to jump-diffusion processes, because the stochastic differential equation I used is closely related to the so-called jump-diffusion processes, which are very well known, especially in finance. And these last 3 papers, the examples I presented come from these 3 papers. So thank you very much for your attention. And that's all. Thank you.
Thank you very much. Please, one question. Marcin, can you hear?
Yes, I can. But I didn't hear the question, but I can hear you.
Okay, so thanks for the talk. I'd like to ask how this passage time scale with when you let A goes to infinity in the last example, where you have this exponential tail for the Brownian motion with reset.
So this is all for large times.
Yeah, I was talking about A. So if you let A goes to infinity, does your resetting time, passage time, behaves more and more like a stable spotinator?
Unfortunately, I didn't check it. I will write it down and I will check it because, well, it's an interesting problem. And obviously, you are right that for large A's, these resetting points could destroy these properties. So you are right. So I didn't check it, but since I have more or less explicit forms for this survival probabilities, I think I will be able to pretty quickly check how they behave for a going to infinity.
Thank you.
But not yet. But I do not have the results yet. A going to infinity. Thank you.
Hello. In your model with time change, when you time replaced by inverse subordinator, you replaced time in Brownian motion part, but not in jump part. It would be natural, in my view, to replace also time in the Poissonian part, and then you'll have a competition of, and there'll be no exponential hitting time because of.
Yes, and if you do that, then your waiting times between consecutive resetting points would be power law. So then we would have very long waiting times for another resetting event, and yes, this is reasonable and it's easy to analyze exactly in the same way. So you can do it by subordination, or you can do it just by changing the counting process n of t to, let's say, for example, Mita-Kleffler renewal process. So the one which has power law waiting time. So this is exactly, you can do it in twofold. You can subordinate an Poisson process, or you can just take the different counting process.
Just a minor point. Igor Sokolov looked at the case where the distribution between the resetting is power laws. There are some are some works on this.
Yes, I know because my PhD students visited some time ago Igor, and they were working on it. Yes, thank you.
Okay, thank you very much.
Thank you, great pleasure.
Okay, so